So looking into the next chapter, which is called as a code generation here. So what is mean by code generation? Code generation is actually the last phase of your compiler, right? So now within this particular once the code needs to be generated, and the last step is actually the code optimization. So once we generate the code, it will be further more optimized, but still we are towards the last phases of the compiler. So code generation is the final phase within the compiler design. The code optimizer accepts whatever the intermediate code which it says, right? Whatever the intermediate code which it sees, once you push it into the code generator, right? Ultimately, the code which you get as a result will be optimized, right? So I have, if you recollect the previous slide there, so we had p1 p equal to a plus b, q equal to p plus q, n number of instructions. All these instructions are actually, most of them are intermediate, right? We don't need, they are just they are only for some time, until unless they are worked upon, and it just moves off, right? So those codes needs to be taken off or waived off. So the code optimizer accepts the intermediate code representation, which is in the general form of the front end of the compilation, and produces another intermediate code representation which is optimized, taking off the unwanted um, instructions which is not required. Code generator takes intermediate representation produced by code optimizer along with the supplementary information in symbol table of the source program, and produce as output and as an equivalent target code. So this is where we were. This is where few of the analysis and semantics happened from here to here, and ultimately the output which we were looking for with the target program. So from the front end towards the code generator, we had our 7 steps or 7 phases. Our code generator is the final phase, right? This was the complete backend. So once we feed the source program, we need to get the target program, which is the machine readable instructions, which should be pretty simple and straightforward for machines to understand. Right? So we have 3 main tasks when it comes to the code generator here. The first task is instruction selection, register allocation of assignment, and instruction ordering. We'll look into the terms of the 3 main tasks independently, one after the other. So instructions selection, in the sense, in the intermediate code we have many number of instructions which are needs to be handled, and there are unwanted instructions which needs to be left off. Once we calculate the instruction, we need to leave few of the instructions, and here checking down those instructions where I can generate the target machine is taken care by the instruction selection task. So choosing an appropriate target machine instruction to implement the intermediate representation statement is actually the main task of instruction selection task. Next is register allocation and assignment. Decide whether the values to be kept in the registry or not, right? So we have hundreds of intermediate values which are taken care in each and every step. So it is our requirement that these values of intermediate will be put into the register contents for every instruction. So if I have, say, some 10 instructions, our registry will be flooded with these values. So ultimately it's the decision whether I am carrying these values which is present in the register for my further processing or not. So this will be the case which will be taken care by register allocation and assignment task. The next particular task is the instruction ordering. So here we try to decide the order to schedule the execution of instructions, in which order I am moving on. So in my execution part. So the next important question most of the time which will be asked in your main examination is issues in the design of code generator. So what are the problems which a compiler in the last backend phase which it can face in its execution period? So one is input to the code generator. What will be the input to the code generator? What type of value will be presented for the code generator? And the target program, what are the issues which the compiler will face while generating the target program? Or in the other words, what will be the output of the complete 7 phases which we have seen before? Next is, what are the instructions which needs to be selected? So basically this is the other 3 are the tasks. So what are the instructions which needs to be selected, and what are the register contents which I need to allocate and which are used to be pushed towards the next phases? The last one is, in which form of evaluation should I encounter if I have all the instructions ready? So that's the evaluation order. So these are the 5 important issues which can be experienced whenever we design the code generator. Looking into the first term here, the input to the code generator. As we all know, the intermediate code will be pushed towards the code generator, right? So input to the code generator is the intermediate representation of source program, where a source program, in the sense, it will be pushed into the parse tree towards the syntax tree towards the our STD, SDT. Then we generate our quadruples, triples, then we get our SAA, right? So once after the SAA, it's all about the intermediate representation of our code. Now we have many symbols and many values to be taken care of. So information in the symbol table that is used in the determining the runtime address of the data objects, denoted in the case of this IR. So here input is equated as IR, that is your instructions, plus whatever the contents which we might be looking into in our symbol table. So instruction representation or immediate representation has several choices. 3 address representation, as I said, triples, which will be the input. So 3 address representation of quadruples, triples and indirect triples are these things which I am looking into as an input to the code generator. Second thing is virtual machine representation, bytecode of some of the memory contents of the stack and its machine codes. Third one, linear representation such as the postfix notation can also be an input for my code generation. The last one is, it can also be a graphical representation such as syntax tree and DAG, which can be an input towards the code generation. So assumptions which we need to look or take care of is, the front-end producers are low-level IR, that is the value of names in it, can be directly manipulated by the machine instruction. So the syntactic and semantic errors have been already detected. So these are the fundamental problems which our the first phase of input in the code generator might be facing. So it's about the inputs which it sees here. Till here I can get inputs with multiple phases, right? Followed by the target program. The output of the code generator in the target program of the instruction set architecture of the target machine has a significant impact on the design of the code generator. So design of the code generator refers to, my target code will be utilized by many types of computers. One can be with the architecture of CISC, and it can also be taken care by the RISC machines, simplified instruction set computers and reduced instruction set computers. So in CISC it has few registers where maximum of 2 operands and variety of addressing modes, variable length instruction and its instruction with side effects. As we all know that in the compiler design, once we see to that these codes are setting out of the particular compiler, it needs to be further processed towards the assemblers too. So in the assemblers, we have many cases of RISC and CISC machines. So all of them have their own architectures in their working. Each architecture depends upon its own working and its instruction sets which it has, which we already have seen in the system software and its applications in the before sessions. So CISC here has very few registers and it has very few working capacity. RISC has many registers and it has many number of operands which it can deal with, and it has much more advanced addressing formats which are relatively very simple with the instruction set architecture. The other case of output can be output may take various forms. That means here one architecture, our compiler will be not only running on one architecture, it will be running on many other architectures. So many other frames has many other own problems within it. So one is the various forms is absolute machine language for the extendable codes, relocation machine language for object files for linkers, assembly language for the facilitating of debugging. So output of the compiler will not be only fixed for one phase or one particular language, it can be of many different forms also. So here the absolute machine language, it has an advantage that it can be placed in a fixed location in memory and immediately executed. So these are the executable related codes where I don't need to be changing frequently with respect to the memory. So it is a fixed location and it will be flushed once the memory will be flushed and when it is executed. Next is relocatable machine language. So this is where platform dependency and independency forms will come into picture. So relocatable machine language refers to I am putting my set of code not in specified areas every time, not in specified addresses at each and every time, but the code will be relocated to many other addresses on the memory, so that there are some changes which happens with the program counter or its dependable register contents. So relocatable machine language program allows subprograms to be compiled separately. The last form here is producing assembly language program as output makes the process of code generation somewhat easier. Next issue itself is an instruction selection. As with the definition goes, the code generation might say that the instruction intermediate representation program into the code sequence that can be executed by the target machine. The complexity of the performing will taken care of the level of the intermediate representation, the nature of the instruction, and the desired quality of the generated code. So looking into the level of the intermediate representation, it will be of high level. Usually the source program will be written in a very high level machine instruction, and it needs to be converted into low level machine instruction. So the use of these templates will be translated each IR statement into the sequence of machine instruction, producing much more simple code and needs further optimization. If the intermediate representation is of low level, using this low level information to generate more efficient code sequence. The last one is the nature of the instruction set architecture has strong effects on the difficulty of instruction selection. Uniformity and completeness of the instruction set has important factors. So in this case here, I have my high level program as x equal to y plus z. So here this needs to be converted into n number of small terms, where first I need to put this y into the register. So putting this y into R0 and adding this contents of R0, because memory to memory addition is not possible in the previous architectures, which are not that much built for it, right? The older locations, the older architectures didn't have that capability of doing machine to machine addition, which most of the compilers or most of the processors which are equipped to do today. So loading the contents of y, or it can be the z also, loading the contents of y to r naught, right? So loading the contents of y towards the r naught, and from r naught adding the contents of y and saving the same in r naught register again. Again, this r naught should be sent towards the memory which is x, so storing it. If you look clearly here, first thing is loading into the register r naught from the memory towards the processor register. The second thing is addition of the contents of whatever existing in the r naught register previously, which was y, right, add with respect to the memory location of z, and again save it in the memory location, save it in the register contents of r naught. So the last thing is saving the register contents towards this, storing the register contents towards its memory location of x. So one instruction which was just x equal to y plus z has been given with respect to 3 instructions further. So this is each particular way how the instruction set architecture might work, right? In different instruction set architectures, it might work in different way, and it all depends upon the processor and its register set. So here, that one more thing is, while using this, it produces redundant load and store operations also. So if I have two particular instruction, that is a equal to b plus c and d equal to a plus d, a and d are my particular values. So what do? B plus c is c or b, I get it into the register content r naught. So r naught is b, then adding with c and saving it in r naught itself. So r naught c. So contents of c will be added with r naught. In other words, it was b and it is saved in r naught, right? So the next case is I have a, right? But here this a has been utilized with the next particular instruction. Should I be storing this a to the contents of r naught to a in the memory location, or should I fetch the value of a towards the r naught? You're getting this? So these statements are not at all required. So these become the redundant cases where storing and again loading it doesn't make any sense, because I am utilizing the value again here. So as again I have r naught here, r naught from plus the contents of b here, this is b, so r naught with b, so the contents will be again saved in r naught. So r naught is what I have. This r naught needs to be sent towards the memory location, so I use store instruction where I send r naught information to the memory location d. So this is about the redundant cases, right? So moving on, the quality of the generated code is determined by its speed and its size. So example instruction here is a equal to a plus 1. So what do we see here? A is a memory location, get it towards the r naught. So I get the a contents towards the register r naught. So next is I need to add 1 towards the register r naught and save it in r naught, right? So r naught here, and 1 is the immediate value, so r naught 1 I add it towards the r naught, and this complete term of r naught needs to be saved in now the memory location a. Instead of utilizing these many instructions, make this complete term into increment a. So this instruction has been now optimized to get one quality instruction, which is increment a. So increment a refers to, we all know that increment a always increment by the value 1, right? So ultimately this single instruction has been converted into multiple instructions, which from has been generated from the multiple instruction. So the quality of the generated code is depending on the speed and size. So speed has been increased because 3 instructions which were actually needs to be fetched into the processor separately and dealt with, and the size of the memory is also cut down by 1 out of 3, right? So 3 instructions have been cut down to 1. So that's about the quality. So register, the last issue here is the fourth issue, right? Register allocation. Instruction involving register operands and usually shorter and faster than those involving operands in the memory. There are two sub-problems here. One is register allocation and register assignment. So select the set of variables that will reside in the register at each point in the program. This is very important. So I need to use those set of variables which I will be using furthermore. The second case is register assignment. Select those specified register that a variable will reside in. So complication imposed by the hardware architecture. Multiplication instruction is of the form where m, x, y, mul, or it depends on the instruction set. So where x is the multiplicand, is the odd register or an even register pair, and y will be the multiplier. It's a single register. So ultimately the product will be occupies the entire even odd register page. So divisor d of xy, here x will be the dividend and y will be the divisor, and the value has two values which needs to be considered here. One is with the quotient and one with the remainder. So as I said here, with the even and odd pair, which is not much used in the multiplier, but our quotient will be stored in the odd register and the remainder will be stored in the even register. A small example here: 2 3 address code sequence, t equal to a plus b, t equal to t star c, and t equal to t divided by e. Optimize code level of the sequence. A, get it in R1, add it with B, and save it in one address. So multiply this contents of whatever you have with R0 with C, right? And this is the division. Whatever ultimately which you have in the R1, save it into the T. So this is the optimized instruction. For this, A plus B, adding the contents of A plus B, then T plus C, again adding the contents of whatever I have with T, this content with C, and stored into the accumulator R0 with the value overall, and divisor value will be R0 comma D, and storing with the contents, overall contents, into the T. So the last one will be your evaluation order. So the order in which computations are performed can affect the efficiency of the target code. When instructions are independent, their evaluation order can also be changed. Some computation orders require fewer registers to hold the intermediate results than others. However, picking a best order in the general case will also be a difficult NP compute problem. A small example here, where I have a plus b minus e plus d into e. I am generating small temporary values here. So a plus b is t1, c plus d is t2. So c plus d, that is t2 into 3, will be t3. Ultimately the value will be stored in 3 4. So this can be reordered in such a way that t2 is c plus d, t3 is c into t2, t1 is a plus d, and t4 is t1 minus t3. Right? Only thing is I have replaced this t1 to come here because I am going from the right hand side towards the left hand side. So all these terms here will be converted into a machine instruction, which you can see here. Move with this case, with this particular case here. So A will be moved to a register, adding with the contents of B and saving it. So that is not further used. So R1 is saved. So C is pushed to R1. Okay, so moving this to temporary T1 because I have T1. So moving the C to R1 register, then adding the contents of R1 and moving this R1 to T2. Alright, so next is, this needs to be multiplied with E, pushing that E into R1 or not, because R0 is now pushed to T1. So R0 is free. Moving the contents of E to R0, then multiplying with the contents of T2. T2 is what do we have? This is R2. Sorry, R1 is having T2 contents. So ultimately, moving the contents of T1 to R1 and subtracting the value of whatever I had with R1 and R0, right? Once everything is done with the subtraction, moving it to T4, that will be my memory location. This is the other way of reorder. Only few more values will be reordered. Why? Because so instead of moving here and there again and again, directly calculate C plus D as the first term. So moving C to R0, adding the contents of D and saving it in the location, right? So it will be in R0. What will be in R0? This complete term C plus D will be in R0. Multiply with the contents of E and save it in. So E contents will be R1 and R0, and I am multiplying and saving the value in R0. Moving A contents to R0 and B contents to adding with B and saving the contents in R0. So this will be in my R0, right? So ultimately this was present in location. So this was also solved. So subtract this complete term was R1, right? So R0 and R1 will be subtracted with the contents, and the ultimate value of R0 will be pushed into the location T4. Here you can see much of the instructions have been reduced, right? That's because I'm not making most of the moving, storing and retrieval operations, right? So that's about it for today.